Welcome. We now want to use the Biot-Savart law to find the magnetic field of current distributions. So we want to first start by sketching, and in our sketch we want to draw our current distribution. As we draw the current distribution, we want it to be as simple as possible, right? If we have a wire, we want to assume it to be a one-dimensional wire unless we're told we can't. And then under this, we want to then draw the current direction to help us with this. Once we have our current distribution, we want to draw the point of interest that we are solving the field for, and we usually label that P. Once we have our current distribution and the interest P, we want to do the same thing that we did with Coulomb's law and build our current distribution out of smaller pieces. So we want to determine the constituent pieces to build the distribution out of. So if we have a one-dimensional distribution, we are building it out of moving point particles. If we have a two-dimensional distribution, we are going to make it out of 1D straight lines or 1D arc lines. So once we've built our distribution out of these or determined what pieces we're going to do, we're going to draw our pieces as slices of the current distribution. And we want two slices in arbitrary positions. Once we've done that, we want to then draw the R vector from a slice to point P. This is if we're using moving points. If we want straight lines or arc lines, then whatever distances we need, whether it's Z or the radial distance, capital R, we do that. And because we really only want to establish a coordinate system after we've done all this, we want to choose a coordinate system and we want to align it with our vector and the direction of the current. We're going to call this ds vector very soon. Quick reminder that magnetic fields are really good with the RTZ system. They oftentimes use that. So don't be afraid to use the RTZ system, aka cylindrical polar, when dealing with magnetic fields. So for our constituent point particles, or if our constituent particles are point particles, then we would have that our differential magnetic field of a point is equal to mu naught IDS crossed with r hat over 4 pi and r squared. So we have that our r vector, if we're in two dimensions, could be rxi hat plus ryj hat. But if we're in RTZ, might be easier to do as r capital R, r hat plus rz, z hat. And similarly then, we want to define this in a variable way. So what can be variable? Variable could be Rx, could be Ry, could be capital R hat, could be Rz. And we want it to be variable such that it defines, right, our R vector for all possible slices instead of just one possible slice. And then we want to define our current I. And lastly, we want to define ds in terms of the same variable in R vector. And a reminder that capital R hat is a function of theta. So we would have it be d theta. So we could have, right, ds be dx, dy, dz, d capital R for straight pieces. In their certain directions, but ds would be r d theta, theta hat for an arc. So this would be dx I hat, dy j hat, dz z hat, dr r hat for these different straight pieces. If it's an arc, then it would be r d theta, theta hat. So as we are solving, the first thing we want to do when we solve is to evaluate ds vector crossed with r hat. Once we have that, we want to find the limits of integration. And then we have a integral. And we could do the integral ourselves, but we've already learned how to do integrals in other classes. We already kind of know it. So what we usually want to do is, right, use a table or a program, either on the web or on your computer, to take the integral. And then we want to, of course, evaluate the limits or bounds. And once we have all of that, simplify. If we have a non-point particle, we want to use the dB of the constituent shape, which we'll be learning about the magnetic field of the different constituent shapes, and we can build it up a little bit later.